Hello everybody, in this lecture we will be solving 1991 IMO problem number 3. Here is a view of this problem. We are given a set S with the following elements: 280 positive integers from 1 to 280. We would like to find the smallest integer n which satisfies a certain property, namely that each n element subset of S contains 5 numbers which are pairwise relatively prime. So we need to find the smallest integer n which would satisfy this property. The main idea, I guess, is that let's consider the following case first. Let's first find a minimum bound on the n. If you look at the smallest primes, 4 primes, 2, 3, 5, and 7, and all the multiples of these 4 numbers in this set S, we realize that you can, for instance, use principle of inclusion-exclusion, if you will, to count all the multiples of these numbers, or combination of multiples of these numbers. You would count, I believe, 216 numbers in S, which are somehow divisible by 2, 3, 5, or 7, or a combination of all these. So if you consider these 216 numbers and you pick the smallest integer n, 216 or lower, it's always possible to find a subset which consists only of numbers divisible by 2, 3, 5, 7, or a combination of these numbers. As a result, it's impossible to find 5 numbers among these numbers which are all pairwise relatively prime. So 216 is not good, it's impossible. The next number would be 217, and we claim 217 in fact does the trick. In fact, it is possible, if n is equal to 217, to find 5 pairwise relatively prime numbers from among all 217 element subsets of S. Okay, so for this, consider the following Venn diagram. We have our set S here, so consider this as the Venn diagram for the set S, and I would like to split this set into 2 groups, those that are composite numbers. So I'll call this portion as Y. This is the set of composite numbers, and as a result, S minus Y would represent all the primes in S. In fact, if you count them carefully, actually, you would realize that you would realize that 220 of the 280 numbers are composite, and so therefore the size of Y is 220, and the size of S minus Y is 60 as a result. The main idea to get the 220, so once you counted the 216 using pi, so to find all the numbers which are divisible by 2, 3, 5, or 7, or a combination of all these, what you do is you take out the 4 primes. So once you take out the 4 primes, you have 212 numbers remaining, but then you add back all the composite numbers, I should say, all the composite numbers which do not have a 2, 3, 5, or 7 in it. We would see that there are 8 of these, namely 11 times 11, 11 times 13, 11 times 17, 11 times 19, 11 times 23, and then 13 times 13, 13 times 17, 13 times, I think 19 is the last one, because 13 times 23 is more than 260. So, and when you add back these composite numbers, which are 8 of them, you realize we would have 220 composite numbers. Okay, so let's randomly take a 217 element subset, let's call it T, of the set S. So T is a subset of S such that T has 217 elements in it, and let's prove that this set will contain at least 5 numbers which are pairwise relatively prime. So first of all, well, we can consider two cases, I guess. First of all, if t minus y, so this part of the set, if t minus y has 5 numbers in it, so if this portion has 5 numbers or more in it, then there's nothing else to prove, right? Because all these 5 numbers are primes, and prime numbers are obviously pairwise relatively prime as well, and as a result we have found the 5 numbers that we were looking for. So for the second case, therefore, for the rest of the problem, let's assume that the number of elements in t minus y is less than or equal to 4. As a result, the number of elements in t intersection y would be greater than or equal to 213, because we know the sum is 217, and as a result, because the total of the composite portion was 220, this side, the number of composite numbers which are not elements of t are at most 7. So we might have at most 7 composite numbers on this side. Now I want to do a very nice trick, and it is the following. I will write down 40 of these composite numbers, and I'll show you how among those 40 it's always possible to find 5 of them which will always be relatively prime. Okay, so consider the following 40 elements. We'll actually organize them into 8 sets of 5 elements each, and that would do the trick, hopefully. So the whole point is to construct this set carefully. Okay, so the first elements would be 2 times 23, 2 times 29, 2 times 31, 2 times 37, 2 times 41, 2 times 43, 2 times 47, and 2 times 2. And then the second elements would be 3 times 19, 3 times 23, 3 times 29, 3 times, oops, that's a 3, 31, 3 times 37, 3 times 41, 3 times 43, 3 times 3. Next we have the 5s, 5 times 17, 5 times 19, 5 times 29, actual 23, 5 times 29, 5 times, sorry for that, 5 times 31, 5 times 37, 5 times 41, and 5 times 5. Now the last 2, 7 times 13, 7 times 17, 7 times 19. All these numbers are composite numbers, as you can see. All I did is to write them in their prime factorization. And so, yeah, so we're almost done now. The last elements in these sets, 11 times 11, 11 times 13, 11 times 19, 17 first, and then 11 times 19, 11 times 23, 13 times 17, 13 times 19, and 13 times 13. We have 8 sets now, 8 sets each having 5 composite numbers. In total, I listed 40 out of the 220 composite numbers inside the set S. And notice that each one of these 5 numbers in each set are pairwise coprime with each other. What matters is that each set, each M sub I, has 5 pairwise relatively prime numbers in it. Now, consider this situation. So we have only 7 elements. The set y minus t can contain at most, so the set y minus t can contain at most 7 elements in it. So you can use at most 7 of these you can put inside this part, meaning the rest would go inside the T intersection Y, so this side, right? So what happens is that you can pick at most one element, so you can pick at most 7 different sets. Eventually, so even if you pick one from each set, eventually one set will be free, and that's it. So that set will be completely contained inside this portion, and instead of picking numbers from this side, all you do is you pick all these 5 numbers and you have your 5 pairwise relatively prime numbers. So and that does the trick. So that's a beautiful construction actually. It's very difficult to construct it, very hard to imagine it, but that does the trick actually. We have just proved that 217 does satisfy this property. So 217, any 217 element subset of S would definitely contain 5 numbers which are relatively pairwise relatively prime, and we are done. Hope to see you in our next video.